Okay, great. So thank you so much for having me. Thank you, Rado, for organizing, and everyone else for attending. Today, you will learn how to formalize all math autonomously and reliably. Yeah, it'll be that good. Okay, not actually. So I founded the UW Math AI Lab back in 2022. It was called the Experimental Lean Lab. In 2024, I taught the first Lean class at the University of Washington. Since then, I think it's been taught 3 or 4 more times by other people. Now I work, and I got my PhD from UW. Now I work at Axiom Math as of June, so 6 weeks, a long time. Okay, great. Let's jump in. So this is a combination of kind of a talk that I gave about 3 months ago and slides that I made for this specific meeting. So let's first talk about what I still think is relevant from the dinosaur era in as far as AI goes 3 months ago. So this is my map of mathematics. I don't know what your map is. You probably have a different one. This one is mine. So we have the core of mathematics, which is the calculus of inductive constructions plus the 3 axioms that Lean uses. And of course, if you're coming from other proof assistants, maybe your core is slightly different. Then we have Mathlib, which at this point is slightly larger, but not by much. And then we have, OK, here now, if I wanted to make this slide today, I would also add something like Tau Ceti or Lean Pool or several other big things. But because this was made 3 months ago, the next layer of this onion is known math, which it's useful to kind of keep in mind this orders of magnitude for these kind of things. So these are the approximate number of theorems. So here you jump by about 2 orders of magnitude. There are about 12 million. Oh no, there are about 10 million theorems in all of arXiv. And then there's of course this last layer of not yet discovered math. And this is a picture from Andrei Karpathy's talk on Software 3.0, where the point was that Software 3.0, which is this LLM-y software or AI software, is eating up the rest of software. So you can replace huge chunks of deterministic complicated logic that was essentially a hand-rolled implementation of some kind of non-random decision tree or decision forest with just a call to your model, where Software 2.0 was kind of classical machine learning models, and this is LLM API calls. And the same thing is happening with math, where formal math is in some sense eating up, except in a very good way, eating up informal math. Except in absolute terms, this is still moving up more than this is moving up. So we got to catch up. Yes?
What about the rate? Like, for example, of course, it's 100 times bigger. But, for example, known math could be growing at a 1% per year.
Yeah.
Lean could be moving at a 3% per year.
Yeah.
I would be interested in what's the growth rate of both. Do you have any estimates?
It's fast. It's exponential. That's formal. That's papers using Lean.
Conservative around 120% growth year on year. Meanwhile, mathematics is like.
I would say that the growth has been like absolutely insane. Like at least in 2026 we already have triple of what we had in 2025, and we're halfway through the year.
Okay.
In 2025 we had triple of what we had in 2024. So the
extrapolation keep it wrong.
Yeah. So we are on an exponential, at least for now. Yes.
One other question. Go back to the slide. Do you have a sense of the order of magnitude within the known math? How much is textbooks versus papers? Like what's kind of the
this is
accepted math in textbooks? That's
this is a good question, and one way to estimate it is the fact that Matlas, which is like TheoremSearch, which I will tell you about in a second, has about the same number of theorems that they search over as TheoremSearch, where TheoremSearch searches over arXiv, and Matlas searches over textbooks and journals. So textbooks plus journals approximately equals archive, although there's of course overlap in the content. So if you were to dedupe, who knows? So let's just approximately say about the same order of magnitude. Yeah, if there are any other questions, that's great. I tend to talk too fast, so questions are amazing. Yes?
So by known math, it sounds like you're actually using a proxy of current papers.
That's correct.
Things that were done this century and perhaps into some of last century.
That's correct.
Anything before that?
So again, we're an exponential. Whatever metric you want to look at is exponential.
I'm
So
actually trying to pin you on something. What is math? And it turns out by your description, the math that you're using, you're starting from a certain information-based database of essentially what's on the internet.
Yeah.
So you may have a database that includes some scanned articles from things that were produced before the internet.
yeah, so
And my thought is that math is actually larger than that and includes a lot more historical information in repositories, which I suspect you are not considering.
that's correct. That is all lost, but the fraction of that is small.
Fraction in terms of what? Bytes, or in terms of ideas, or in
Any
terms
metric.
of representation?
Any metric,
Okay,
the
I
population.
challenge that assertion.
So the population of Earth has increased exponentially in the 20th century. The number of mathematicians has increased exponentially. The number of papers per person increased, maybe not exponentially, but significantly. So that all amounts to the fact that the amount of math that's been produced in the last 50 years far outgrows the amount of math that was produced in the all previous years.
By your particular measurements where you're actually measuring bytes, because I agree with you, not very many bytes were produced then, but they used different technology.
That's right. I'm not saying that those people were stupid. Those people were very smart.
No, but also I'm saying that you're actually not considering that in your particular map of math, and that's fine if this is what you're starting out with, but there should be a nod to some of the historical productions as well.
Right. So
You take a challenge after the talk.
yeah, I am happily discarding all of that.
Okay. I'm
Yes.
not happy, but
That's okay. That's okay. Not everyone needs to be happy. So, okay. So how do we formalize this onion? How do we speed up this process of the formal math eating up informal math? Well, there's okay. I will argue that the bottleneck is actually not intelligence, not anymore. I would say that the bottleneck is actually the dependency issue, which is the fact that if you have to prove something about some object and the object is not defined, that is kind of the toughest challenge. So if you have a theorem whose and you can kind of think of two dependency graphs. Here I only picture one. One dependency graph that is on the level of statements. You cannot even state the thing before you have definitions of some other objects. And one on the level of proofs, where you cannot prove the thing, at least if you follow the known proof, without certain objects. And of course, the graph on the level of proofs will be it will have more edges. So anyway, this is my picture for what this dependency graph looks like. This is informal mathematics. This is formal mathematics. And I would like these two graphs to be connected. So this graph, there's it depends on your design choices, but essentially it's pretty straightforward to extract that. Which talk to Evan if you want to know more. And the informal one, there's a lot more design choices that goes into it. So of course you can go through all the LaTeX sources and you can parse all the /ref and /cite, and that gives you some idea deterministically. But then of course there's a bunch of implicit dependencies that to do this properly you would have to capture. And capturing that well is tricky. Capturing that well at scale is tricky. But in the project that one of the things I will talk about is exactly our attempt at doing that. And what I want is to identify which nodes in the informal graph are also exist in the formal graph, so that this kind of creates this global blueprint of mathematics, where if something is far away from all known formal math, perhaps it's hard to even state. If something is close by, perhaps it's a good next target to formalize. There are several hints. Yes.
Yeah. So maybe I was gonna. Are you gonna talk about the fact that it seems that the informal one is not actually well defined? There are
That's correct.
variants of definitions.
That's correct.
Are you gonna address this later?
Yes.
I think
Anything else? Great. So let me tell you about, so this talk has like, I don't know, 5 papers in it and 5 other projects in it. So I'm trying to move quick. And if you want to learn about any one of them, talk to me afterwards. So TheoremSearch was kind of our first attempt where we didn't have any graph structure, but we just made a search engine. So what we did is we went over all math papers or math and non-math papers on arXiv, anything that has some theorem environments in them. And we took the LaTeX sources, we extracted everything inside of theorem environments as well as lemma environments and definition environments and all of these things, and anything that is like an entity that could be a node in that graph. And we built a search engine over this corpus. So again, this doesn't have any graph structure, but already we found that this search, just a semantic search, so vectorized database. Many of you work in software, so you probably know how that works. In short, you embed the text into a vector, and then you do cosine similarity between vectors. So at the time, this was January this year, we saw numbers that are about almost twice larger than LLM-based search, not to mention that LLM-based search would take a minute, 5 minutes to go and search the internet and find the relevant stuff. Whereas this semantic search is essentially instantaneous because all it does is compare the cosine similarity of many vectors. Since then, LLM-based search improved, and I don't have the numbers for you. I wouldn't be surprised if it's approximately the same now, or maybe even GPT 5.6 might even be better. I don't know. I did not compare. And these numbers are on the benchmark that we also created for this problem, because essentially no one has done something like this before, where we asked several professional mathematicians to take the papers that they know well, understand well, and say what kind of thing would someone search for to find this given theorem. And we have we have the full benchmark published. So if this description was not satisfactory to you, then go to theoremsearch.com and just look at a few examples yourself. They're quite reasonable examples.
Could you do me a favor and interpret that first line? Google search 0.378 or 0.378 is in the column hit at 10. What does that number mean?
Right. So this means that if you take one of those search queries from our benchmark, and you see what percentage of the time the target paper appeared in the top 10 Google results, that is 37.8%.
Oh, okay.
And the reason why this number is so small, even though Google search is really, really incredible, is because Google over-indexes on the title and the abstract and under-indexes on the rest of the PDF. So I actually used to think that it doesn't index those PDFs at all. That is not true. But somehow it just like really kind of under-indexes them.
So hit at 10 means hit at top 10.
Yeah.
Okay.
That's right. Good question. Then the second part of this project was Theorem Graph, where we added the graph structure. So before we only had this kind of embedding from text or from theorems into this large latent vector space. Now we also add the graph structure. So this is another visualization of what that might look like. You have a smaller number of nodes, and you cannot see the edges here, but there are edges. The projector is playing tricks on you. So there is this formal graph. And here, this is not just Mathlib. So we took a bunch of popular repositories, 25 of them. Although, of course, Mathlib was still the majority. I don't know if I think Mathlib is probably not even the majority of lean code anymore. But at least at this point, that was like late April, early March. I think late April, when we actually did the data collection. Yeah, the world was different. The world has really changed in the last 3 months. And this is our informal graph. How are those edges collected? Of course, the first step is to parse, do the deterministic parsing. So the /ref/cite. And when you do /cite, of course, it cites the whole paper. So somehow you have to figure out which specific theorem is being cited. And that is not easy. but we did our best. So in particular, if right next to the /site there is, theorem 3, then okay, often it doesn't say that, and then you can kind of like, so we make a cheap call to an LLM to try to figure it out. It's not perfect. So none of this is perfect. The amount of money we spent on this, it was an academic budget. So if you actually, we have a portion of this data set published. The reason it's a portion is because of licensing. About 85% of stuff we couldn't publish because of restrictive licensing. But if you look at the portion that we published, like some edges are quite reasonable, some are not. We did our best. So anyway, first was deterministic. The second one was also deterministic, but heuristic. So we looked at things like the theorem above or the following result. There are kind of, math language is fairly low entropy, right? So you can kind of collect 10 of such heuristics and you capture some non-trivial proportion of those kind of dependencies. And then the last one was LLM-based, where so we couldn't afford to feed, a whole paper into an LLM like that. If you actually calculate how much that costs, it's just too much. So there is 700,000 math papers in archive. If you pay $1 for each one, our lab does not have that money. It's not even close. It has to be like 100 times less than that for us to be able to afford that. Even a little bit more than that. So we had to be very clever with exactly what context we pass into the LLM. But anyway, so those are kind of 3 tiers of edges, and at the end we ended up with what? This says 11 million. I think this is wrong. I think it should be 18 million. I don't know where 11 came from. But oh, sorry, I'm looking at the wrong number. It is 18. Yeah, good, 18. Okay, great. So that's theorem graph. Yes.
Do you have a sense? I assume it's like 90%. But what's archive representing all of mathematics? Like, I assume some people don't put their papers on archive. Do you have a sense of?
Yeah, correct. So I would say it's maybe 50% of, if you collect all other sources, maybe it doubles it, maybe it triples it. That's the rough order of magnitude. Yeah. Yes.
Is there something to be said about how you were like identifying which theorems referred to the same thing, modulo like little differences, and saying like this one cares about like is a topological definition of limit, or all those sorts of.
Good question. No.
So you just didn't care about that. You skipped over that. So these are 2 different theorems.
Correct.
Okay.
I know it's bad. I mean, it's just more work to dedupe, because when you try to dedupe, now you run into all kinds of issues of like, oh, this is a slightly this statement is slightly different from this statement. Are they really the same? Depends who you ask. So it's just like there's more design decisions that we did not want to do. What we did do, which I think I forgot to mention, but this is actually kind of the central point of the paper, is that, or maybe I did mention it, which is that we matched these 2 graphs. So we have something like 40,000 links that we identified between both of these, where by a link I mean that this node in formal mathematics, for example, MATLib, and this node in informal mathematics are really stating the same thing.
So do you use LLM embeddings? You said previously. Did you try your own embeddings? Or I know people claim that simple embeddings work very well for some of these things.
Yeah, we use Qwen 8b, Qwen 3 8b embedder. Yeah, we in the paper we have a comparison with more embedders, something like 4 or 5 embedders. So you can take a look. Qwen 8b works the best. Yes.
Do you have any notion of the value of a relation between the 2 points? Like, obviously it's very impressive to have a graph with lots of vertices. But is there any particular notion of edge, value of edges that you're trying to explore through the graph?
Value, it's a dependency graph.
Like some relation R that's it depends on or is related to.
Depends on. It's all depends on.
Yeah, dependencies.
It's only dependencies. Yeah. Yes.
Do you have an idea of injectivity? There's a very different number of nodes, and so when you're doing matching.
Yeah, this graph is way more dense,
Yeah.
at least the way we constructed it.
Yeah. But when you're doing matching, is it one-to-one, is it one-to-one, or is it multiple things?
Matching between these 2 graphs?
Yeah.
Not at all. Not at all. Not even close.
So is there I don't know, I would be curious what node gets
Good question. The dataset or a portion of the dataset is published, so you can take a look and just open Claude and tell it, here's the dataset. Find me the node that has the most, the highest degree. Yes. Or yes.
Yeah, I was wondering if the number of edges per node has changed over time, because I was thinking maybe there's a fundamental property of mathematics that the moment that we formalize all of human mathematics up to this point, we will achieve like in this construction a particular number of edges per node. And I was wondering if that value, which is of course very dense compared to the informal, but if that value was oscillating or if it's converging to some number over time as you add more and more, because it could be a fundamental property of mathematics.
I don't understand because each node has its own degree. So what do you mean by one value?
There's an average number of edges per node, right?
Sure. It's 11 million divided by 388,000.
Has that average changed? Like for example, are the number of edges growing faster as we add more?
Yes, of course, because it's not a tree.
Okay.
Right.
So is there an expectation of what the overall value is going to be once we have formalized all of mathematics?
I mean, the larger the graph is, the larger the average degree is.
Yes, of course, but is there for example, it's growing quadratically, so we should expect that mathematics is going to be very dense?
It's certainly not quadratic because it's not a complete graph. Mm-hmm. So, it's between the two. I don't know which one it is.
Okay, so it's not.
We only have one mathlib. I mean, okay, here's a good experiment. Do this for mathlib over many, many versions, including mathlib 3. It's hard to engineer this. Even Evan is laughing because he did the metaprogramming for this, and he really struggled to make it work for different versions of mathlib. And I think he only went down to 428, 427.
I managed to get it to work from 4.24 to 4.29.
Okay.
And then below that, the metaprogramming just breaks too much.
Right. So this is when I say it's easy to extract the formal graph. It's only easy, it's not actually easy. So making this work is not a trivial challenge. If you can make this work, you can probably write a paper on that thing, or maybe with a little bit extra beef, that is a good exploration. But this is not something we've done.
Yeah, of course. I was just wondering if you had done it before.
No. Yeah.
But we will expect when the formal graph is full, it'll be denser than the informal. Right?
Correct. Any statement that has an equal sign in it depends on eq.ruffle. Any statement that has 1 in it depends on nat.1. So yes, that graph is pretty dense. And Evan did his
pair of nodes in either graph where you can establish that there will never be an edge.
No, it cannot be the case, because that way it would mean that it's a piece of mathematics that is in no way connected to the base of mathematics. And that would be, I suppose you can choose a completely different set of actions, but at that point you're not talking about mathematics. They have to be connected.
Yeah, this graph is connected.
Really, it speaks to the nature of the connection. So it speaks to the nature of the edges that they're drawing. And so my question is actually pointing at, do they understand how they're putting edges together well enough to be able to say that they'll never connect those two? And I think the answer is not yet.
Yeah, so please take a look at the paper. I think there's a big discussion there on exactly the design choices that we make when we draw those edges.
Right.
Yeah, good question. Let's move on. So, slides from today, and the first portion of slides was supposed to be a fifth. So I'm going to move even quicker. Okay, here's my central claim. Intelligence is no longer a bottleneck. And I will try to prove it to you a little bit. And the bigger question now is how to make this actually useful, how to make AI formalization actually useful. So I think we're kind of past the point where it's 3 months ago or 6 months ago, we were in the world where oh, let's see what model is the best. Oh, can it even prove this 1,000-line code, thing? Oh, it messes up basic syntax. Well, I guess it's useless. We're way past that. We're in the territory where if we're not harnessing this, godlike power, it's just like we're just like shooting ourselves in the foot. So the question that that I'm much more interested in now is how to actually make this useful. So all these benchmarks, great. I say, we keep them, of course, but like essentially they're saturated. With enough test time compute, okay, not everything goes down, but like many things go down. And I will show you some examples. Kevin Buzzard really disagrees with me, so I had many discussions about this on Zulip, and this is just my opinion, and we can talk about it and have a great debate. So how to make this useful? Well, there are several projects that, and I will talk about a couple of them. Then another question is, for it to be useful, you need to have trust. And with humans, you just trust that like when you say, when you see the definition of, cont diff in MATLAB, it means continuously differentiable, right? Well, okay, sometimes it doesn't work because cont diff at top actually means analytic. So sometimes MATLAB throws a curveball at you. But most of the time, you can trust that the definitions are sensible, and the humans who made them, really thought things through. So how do we gain the same level of trust, or at least similar level of trust, in AI formalizations? That's a question that I will try to address. And another question is how to present an AI formalization project and how to engage with it. So right now, a big issue is, OK, if you look at AI authored projects on Zulip, there's about 2 per day. And each one is like 10,000 lines of code. And it's just a lean repo. And often it doesn't even have a comparator. It doesn't even have formalization.yaml, right? And those are like the most basic things. And I would argue that that's not even enough. Like that doesn't even tell you like that much. So we're just like being overwhelmed by this like deluge of AI formalization projects. How to present it in a way that invites people to engage with them? If you're not being invited to engage with it, how do you engage anyway? What kind of questions can you ask? How can you audit? It's all kind of the same sort of questions. The second and the third question are very similar, and I will try to address this a little bit. So you've already seen this slide. This is a graph from Sunho from AWS, and okay, you cannot see this projector really is not that great. I think this is even I cannot see. I think this is January 2025. So this just captures 2025 and 2026. This captures from 2015 to 2026. And these are the number of papers with Lean. So especially looking at this graph, I see an exponential. So that's the world we live in now.
Just out of curiosity, the top graph per month, you have 2 different colors. And it's suggesting, especially if we're worried about the colors down there, at that month, something changed and the world became a new color. Can you explain that?
Is the year. The year change.
Just the year.
Yeah.
Okay.
Yeah, this is December 2025.
All right. Putting both of these on the same slide. Okay, thank you.
Okay, I would like to request comments that are more substantive. Thank you.
I understand.
Great. So in the early days, 3 months ago, those are the kind of things that I was proud of. I was very proud when I posted this message. It was 2 a.m. I just finished that formalization. I just got all the interesting stats about this formalization. I was like, wow, I'm just like Math Inc. now, except, I can just open source all of this. That was like right around sphere packing, right? You all know about sphere packing, right? This is like 10,000 lines of lean code. I would never write that by hand. And it formalized this theorem that I just got in my most recent research paper. That is amazing. And that theorem is this one. Yeah, so the equilibrium of Maxwell-Vlasov-Landau system, it's a system of PDEs that describes the motion of plasma, which is what I worked on in my PhD. And it states that the equilibrium is unique and it's a global Gaussian. And we can talk more about what that means. I think this is maybe like going too much into the detail here is not for this talk. But that is the kind of thing that I was very, very proud of back in March. Then in April, Brian Nugent and I, Brian Nugent is now at MATLAB Initiative working on StacksLib. Back then he was not. We wrote this paper, which was essentially the same kind of experiment as this one, except we didn't just get it to compile. So here I was like, wow, it compiles. I'm the best, you know? OK, like, of course I didn't do anything. I just like prompted AI. But still, I was very proud like that I discovered that it works. You know, it was like I don't know, I guess like even like having to remember back because now it's like so not interesting, right? Now it's like, OK, duh. But back then, like late February, early March, you know, sphere packing was such a big thing. And you know, it was like a mystery. How did they do it? Well, it turns out you can just prompt and it just does it.
There were people who were saying this would not work so easily.
Right. Exactly. That's exactly my point. I was like, wow, this works. You can just tell it, like Boris said, just continue. And, we didn't have /goal back then. You know, the world was different. Now we have /goal, and Codex actually respects it. Code doesn't, but Codex respects it. It will actually work for 2 weeks until it accomplishes the goal. So right. So here we didn't just get it to compile. Brian heroically reviewed all this AI code as if it's like a MATLAB contribution or something like that. And then I fed that huge review to Claude and iterated on it for another 2 weeks in a semi-automated fashion. You know, semi because I still had to type continue a few times. So that was like, you know, I wanted to understand what is the ceiling of like the code quality if you give it a pretty detailed review from a very capable human. So MATLAB. So Brian has contributed to MATLAB a few times now. He is very familiar with the process, and this exactly that project was exactly in the same area that his MATLAB contributions are. And our conclusion was that the definitions are still really bad. The lemmas are much better after the review. The file names are much better. The placement of things is much better. But at that point, it still like wasn't working very well. So that was.
When you say bad, you mean bad in a mathematical sense or in a kind of software sense?
Both. Just way too specialized. Like if again, take a look at the paper. We have some very explicit examples. We have like 2 pages of like specific examples. Brian flagged one specific example that was like really bad, whose name, like that name, like the name of that lemma contained H1, where H1 was a hypothesis that was somewhere else in the project. So like literally the name of the lemma had like H1 is obviously not. Anyway, it was bad. Fast forward 3 months later. Oh yeah, that was 3 months ago. That is today. 10 times more in 10 times less, right? And you know what? I feel much less proud of these announcements than I felt of that first announcement. Where's my announcement for green tau? Yeah, green tau theorem. So tau is inherent tau. This is like a super celebrated result that primes contain arbitrarily long arithmetic sequences. 1 prompt, 1 day, 24 hours, 100 lines of code, 100,000 lines of code. It's not even it's not even interesting anymore. It's just like you just do it. It just does it.
You're not gonna claim a super fancy harness and.
No. No. 1 prompt.
Yeah.
1 prompt.
With like vanilla codecs or.
Yes. You open Codex and you do /goal, formalize green tau. You wait for 24 hours. Yes. Yeah. Just very different world. What is this showing? I don't know what this is showing. Oh yeah, this is showing. I don't know how to pronounce this. Boris, do you know? Zmeridis. Zmeridis. Okay, Zmeridis. Okay, Zmeridis theorem. which I actually don't know what it states. My prompt for this was even worse. It was find an easy statement in Lineval and prove it and submit it and make sure that it appears on the leaderboard. And this whole thing took 2.5 hours. Out of 2.5 hours, it spent 48 minutes actually like making the informal solution, making a blueprint, and formalizing. And it spent the other 1.5 hours waiting for the CI on Lineval to finish. and using browser use to like click around to make sure that it appeared. Right. So, by the way, all these 3 examples were previously unsolved by any model on Lineval, including GPT 5.6 Sol, including Seed Prover, including Harmonic, including all of those. So I tell it just pick one that is unsolved and solve it, and it just does it. Anyway, what's really interesting here. So I really like this finding. To me, this actually is the most valuable part of this whole experiment. So I asked it for different stats for Archimedes theorem, and it told me it was 42,000 lines of code. And then it said, but only 275 of those are new. And I was like, wait, where did the other 42,000 come from? And it said, oh, I just took your formalization, I just kind of reused the stuff from Green Tau. This is a new thing to me. It was able to fully reuse all of that code. So what does that tell us? It tells us that somehow like those lemmas are not like super mega specialized. I mean, to be fair, I then asked it a little bit more, and it turns out that this theorem is somehow like part of that. So this is maybe not the best example, but still, like, it's getting there. I want to do more experiments like that, and see how much it ends up reusing stuff. In my prompts, I also tell it like reuse Mathlib, reuse TauSteady, reuse LinPool. If you find some other GitHub repos, reuse them. So I really want to see this reuse come into play, and I will tell you more about reuse in a second. Yes.
Did it find it because it was done by you, or kind of searched GitHub?
I'm guessing. I don't know. Yeah, I have no idea. Like, it's really hard to tell, right? Because it's too much.
Did it say that it used the repo from earlier?
Yes.
Okay.
Yeah.
So somehow it knew about it, whether you told it or it was in a neighboring file or something.
Well,
it said that it used it.
For example, Codex has memories. It writes memories, so it knows that we just did the Green Tau. It can also search the internet. Could be either of those. Okay, I don't think there's anything interesting here. Oh no! That was my first. That was my first example where people in Zulip were like, no, we still don't have enough data. Like, oh yeah, my claim was like, well, if you just throw enough compute at it, it will work. It will solve it. And Kevin Vassar was like, okay, what about FLT? Which, okay, fair. We're not there yet. Like, I'm not crazy. Like, I don't think that you can just /go prove FLT and wait for a month. Like, I actually don't think this will work. Maybe with the next iteration. We'll see. We'll see. We'll look out for the next announcement. But for now, I don't think this will work. But I did want to kind of make my point, and so Brian at that point entered the conversation and was like, well, my problem is still unsolved. And I was like, okay, let's make a bet on how long it will take Codex to solve it. So Brian said 7 days. I said between 2 and 3 days. It was 1 day. So we're both wrong, including me. Okay, switching gears a little bit. Question: how to present not just formalization, but AI-driven formalization? So I'm really interested in this because, again, we live in a world where these formalizations appear faster than anyone is able to digest them. People don't look like, many of them have some very non-trivial math being formalized, but no one cares. It's just too much. So how do we kind of engage with this? So I'm really trying to find a form factor that would be kind of human digestible. And I stumbled upon, how did I come up with this is, if you've seen the Hugging Face blog on how they were attacked by OpenAI, sorry to point at you so much, Boris, 2 weeks ago, they have this very nice interactive visualization of how the attack progressed. And I thought, oh, how cool would it be to make a similar thing for like the progress of AI formalizing something instead of attacking something. And so this is this, let me zoom out a little bit. This is this like movie that it made where like over timestamps, I think the timestamps are too high for you to see, but over the course of 25 hours, this is the order in which it took. And I know that you cannot read this, but if you go on your computer, you can actually read what those are. And I don't know this mathematics, but if you do, then you can kind of see like, okay, it actually decided to take this path over this other path.
Each box is like a named result.
Yeah. Or it's not quite named. Like this is a little bit like some of these are named. Like I see the word Euler here. Euler completion. I cannot read this. It's too the quality is too bad. Euler completion tail. I don't know. Like okay, this is not CFZ dense model. Yeah. Box moment bound.
I guess Tao was interested in formalization, and have you gotten feedback from him?
Who?
This Tao himself.
I don't think you saw this.
Okay.
Yeah. I mean, it's too much, right?
That's all. Well, this visualization, for example, like you got feedback from somebody who actually.
Well, I mean, I don't want to be like at Terrence Tao. Take a look. Like.
Yeah.
It's really nice. You should just do it.
Yeah. I mean.
I know. I've DM'd him, but like, I don't want to do it in public like that.
He's formalizing something else. So I don't even know if this is something he was planning to formalize. Like he's doing PNT plus.
Yeah.
So just make an announcement. I'm experimenting with formalization.
Oh, I have.
Right.
Yeah.
And,
Yeah. I've been annoyingly active on Zulip in the last 2 weeks.
If he's interested, he'll look at it.
Yeah. I agree. So that was finished. So what is my point here is, I don't know. Maybe this is a nice form factor to present a formalization. A bunch of stats that people will ask about, and a movie, and important statements, and like the path that the AI followed. So these are different papers. So this is a paper by Green and Tao. This is a paper by Tao. This is a paper by some other people who I don't know. Anyway, whatever. So maybe this is how you present it. I don't know. This is a not yet finished project, and okay, this is a big site, but my favorite part of this site is this graph, where each node has. Okay, this is probably way too small. Like you probably cannot see this at all, right?
You can see it now.
Okay, so you can see that each one is assigned some points. So this is kind of the biggest difference from Lean Blueprint. That there are these points, and there's also status of whether it's blocked or not. Well, okay, I guess that is similar to Lean Blueprint. And yeah, the point is to collect all the points, right? So then when I ask, so a big benefit of that is that when I ask it, what percentage is left, it can kind of look at these points and be like, okay, that percentage is left. But of course, the assignment of points might be wrong.
Wait, so this is not done, and you're planning to open it to open source contributions, or is
this is public, so if you want to make a PR, make a PR.
Okay.
So
your goal is to get more, because there are lots of people interested here. You want to get more involvement with this?
Sure. Yes. Everything I'm showing you, please get involved. So.
Are the points machine generated or human generated?
Oh, it's all machine. I don't know this math at all.
You don't know if it made up some theorem that's not true.
Oh, correct. Absolutely.
So you get the last step, and then it'll be like.
Absolutely. But at this point, if a human disagrees with the AI, with the GPT 5.6 Sol, I would actually rather trust Sol. I'm not joking.
That's not the problem I'm talking about. It would be addictive if it gets to the last 3 and it looks like it's about to be finished, and then it doesn't finish, and then.
Yeah, my point is like, the models are quite good now. So
Are you that you have formalized statement correctly?
So the statement was given to me by Kevin Buzzard.
Oh, I see.
So the statement is not very hard.
Yeah. So the reason that I want to do Mazur is because.
Source of elliptic curves, right?
Yeah.
Plus, yeah.
Yeah. So the reason that I want to do Mazur is because, what is it like? This is so I think Kevin Buzzer was like, okay, there are these two assumptions that I have in my FLT project right now, and I have many more that I cannot state, but these two I can state. And he was like, maybe one of them is doable. And the one that he said is maybe doable was done in less than 24 hours by some random guy on the internet. I don't know who it is, but that I put up the challenge. I don't even know. I don't look at it anymore. That's the thing. That's the crazy thing. To me, the significance is not the math anymore. To me, the significance is the social aspect. The fact that it is there's so many open questions, and each of them or most of them I can just tell /goal formalize this, and it will. So okay, to me, the value is more like, okay, this is on the path to FLT. Like that is what gives it value. And so I put up the two challenges, and within something like 16 hours, one of them was solved, 30,000 lines of code, and Kevin the second one, Kevin was like, oh, this is like way out of reach, like no chance. That's Mazur. Except some other guy. I don't know who he is. I think Andrew Yang. I've never met him. He's like, oh yeah, this is trivial. So somehow it's both impossible and trivial at the same time. But Kevin says, yeah, this is way too hard. And I told him that I want to chat over video chat, and he was like, I'll meet with you once you do this. So my purpose in life is now to do Mazur. I mean, in reality, I spent 20 minutes like just telling it, make a blueprint. Okay, blueprint looks good. Okay, start formalizing, like this kind of thing. Dispatch 3 agents to start formalizing. So,
but you're making it. I guess you can also finish it yourself. I guess, but it seems like you're trying to make it a community effort.
So the problem is I only have 3 subscriptions, and I'm paying $600 per month for those. So that's getting a little bit steep for me.
We all can relate.
By the way, but the OpenAI thing, the 100,000 people, like the when you apply, it auto rejects you. So that's a bug or some issue, I don't know. So someone has to fix it. Like I have a pay slip from my university, and it's not accepting it. So I would like to pay less. But still, right now I pay $600 for 3 subscriptions, and I max all of them out every week, and I kind of don't want to get more right now. Yes.
What subscriptions you got? Like, what's the stack?
Oh, I have 1 Claude and 2 Codex. Claude is kind of bad right now, so use Codex. Before GPT 5.6 came out, Codex was awful. Claude was really good. So it changes every month. It changes.
Have you tried
Yes, I tried it on some toy thing. It was really bad. Yeah, it's both very slow and very token inefficient. Yeah, and also there is some issue with, I think, what is it? It's hard to get on. It's actually somehow hard to get the subscription because they don't have enough capacity, something like that. Anyway, yeah, in my mind. Right now, Codex has really good value out of open source. It's not open source. Out of things that are not in beta testing. I mean, for example, Aleph is also good. For example, Axiom Prover is also good, but you cannot get access to them just willy-nilly. Okay, great. So this was we talked about how to present a formalization, both finished and unfinished. And I don't claim moral superiority here. I really want people to experiment more with how to invite others to engage with this content, because otherwise we will just have this continuing deluge of AI formalizations and nothing useful comes out of it. Yeah, absolutely nothing. Okay.
There's 2 types of others, though. There's a professional mathematicians who understand some of the math but don't know lean, maybe. They're not into the engineering things, and there are also a bunch of us here, hobbyists, for example. They're willing to contribute, but they don't know maybe as much of the math. And that interaction, if we talk about that interaction, actually, I think is the hardest thing.
Right. So I think the important thing here is to somehow direct people's efforts into something that is actually useful. So we need more things like formal conjectures, like Erdos problems, like lean pool, like Tau-Ceti. Each of them fills a slightly different niche. But I mean, arguably, Erdos problems don't lead up to anything. But Tau-Ceti actually leads up to something. So if you spend your tokens on Tau-Ceti, like that is like a real contribution that code will be reused by others. Whereas when you just like formalize a random thing, okay, that doesn't do anything. And so, well, in a second, I will start telling you about lean pool, which is so lean pool appeared 2 months before Tau-Ceti, or no, 1 month before Tau-Ceti, and that was my attempt to collect people's efforts. But anyway, before I tell you about lean pool, I wanted to talk about another way of presenting an AI formalization project. So, okay, a nice visualization is great, but how about some hard statistical quantities? Things like the average degree. Several people have asked about this kind of thing, like because if the average degree is high, okay, I guess you have some reuse, right? Like, I guess you're not kind of reinventing the wheel all the time. Or like, are you actually reusing mathlib? That feels like something you can quantify. Well, so I've computed something like 20 different metrics on something like 20 different repos. And overwhelmingly, the conclusion is I don't know a good metric, even though it feels like there should be one, or 2 or 5 or some combination. No, I can't find it. I just put 3 that I thought would are like produce nice graphs and like interesting to think about. So which one is the easiest to start with? This one, elaboration cost per 1,000 lines of code. Wall clock time, like if you compile the project and you just, how long did that take? I know it's CPU dependent, so this is all on one CPU. So, and it's still not the best, but like the error bars are somewhat small there. It's not going to be a factor of 3 on the same CPU. So you just take that and you divide by the number of lines of code. And the idea is, well, some people can write more efficient code, some people can write less efficient code. Maybe AI, maybe like good code is more efficient. Maybe it elaborates faster. Mathlib sits kind of in the middle. Tau-Ceti is a far, far outlier. It elaborates very slowly. I'm actually not so surprised because I think Kim doesn't have a profiler in Tau-Ceti, which I think should be changed. In lean pool, we have a profiler. Every PR gets profiled. She only has a radar, and I'm not sure anyone even looks at it. So I'm not surprised by that. I'm also not very surprised by CSLib because the kind of arguments there are like very different. But like, would I expect mathlib to actually elaborate the slowest? Well, maybe it's because it's very deep. I don't know. You can come up with all kinds of explanations. But then physlib is much smaller than mathlib, so why does it elaborate slower than mathlib? And then FLT is right here, and then PFR. Like, I don't see any kind of obvious pattern here, except that like these are all human written mostly. Lean pool is actually the majority is human written. Fun fact. I guess I haven't started telling you about lean pool yet. But like these are all mostly human written, but then Tau-Ceti is not, and it's on the other side. So I don't know how to make sense of this.
What do these numbers?
Elaboration time, how fast the code is.
You mean how fast the code compiles?
Correct.
Is elaboration the full? Isn't there also elaboration and actual checking with the kernel? Are the 2 phases, or my understanding of the
I think.
build is
So I think this is like the full thing, like
full
to
build.
compile to I think
just
this.
to do lake build.
Yeah. So I think this is exactly done with lake build -- profile or whatever that command is. Right. You can try to reason through this, but my point is there's no obvious pattern. And I have 20 metrics like that, and short story, there's no obvious pattern. Okay, let's move on. Okay, this doesn't fit in the story, but this is a good side quest. Golfing. It would be nice if there was like a very easy to measure quantity that tells you the code quality. When you ask, oh, I haven't put the mathlib conventions here, but that is also a fun experiment I've done. So the problem is, when you make a mathlib contribution, if you use AI, people will say it's bad quality. Then you ask, well, what if I clean it up by hand? Which I've tried. they say it's still bad quality. I'm like, okay, what does it mean? Like, what is bad quality? Like, and they're like, you know, they cannot say. Yeah, so I'm like, okay, I'm gonna help myself. I'm gonna go through all Mathlib PRs. I'm gonna kind of use a cheap model to summarize the reviews on all of the PRs, 100,000 reviews, and then try to distill them into some big categories and try to, like, you know, essentially distill the Mathlib maintainer's knowledge into kind of a set of rules. Anyway, that failed. No one cared. People said it's bad. So I thought, okay, what's another way to measure code quality? What is the most, like, what is the one thing that everyone gets on their Mathlib PR? Well, goals. Like, people love to go and say, you can write this thing instead of 5 lines and 3 lines. So it's better. I mean, it's not always true that golfing is better, but it's almost always true that it's better. And so I thought, okay, this is like easy to measure. So how about I just tell AI to go and golf? I've done this on LeanPool. I don't have a picture here, but on LeanPool, it golfed about 5% of the library. Then I've done it on FizzLib, which this was actually merged by Joseph Tooby, the creator of FizzLib and maintainer. So this is a golf by Opus, and then there is a golf by Fable. Fable is very, 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 very good at golfing. I have not tried GPT 5.6. GPT 5.5 was really, really bad, to the point that that PR was not even merged, even though it was a golf. It was just like, you can look at it. But anyway, yeah, this is my rating. So if you were to evaluate models based on how well they golf, Fable, incredible. Opus, quite good. Really bad and really bad. Right.
You said it's better, but like, I mean, what do you use as definition? I get it, like Mathlib likes that, but I guess coming from other software, like actually I'm surprised that golfing is so highly, because when you write a good software, sometimes super like there's a reason why we don't write.
You're asking like why Mathlib cares so much about golfing?
I guess, what's your opinion? Like, do you believe that's better, or you try to match what Mathlib has given you as a quality?
Oh, I think this is a nice way to this is a nice proxy to see how well AI can improve code quality, not just race to the finish. You know, these models are all RL to death. You know, if the thing compiles, they get a reward. Okay, I don't actually know how they train it, and we have someone who does in the audience, but they will not tell us. And so, you know, in my experience, they're RL to death, and anything that is kind of outside of a verifiable domain, it's really hard. So I find that GPT-5, the way it golfs, is really awful. But the way Fable golfs is really incredible. So in my mind, this is like a way to gauge if I were to use this model to improve the code quality, which is not a verifiable thing, like what can I expect? And I've tried to do this for compilation speed as well, or elaboration compilation speed as well, like build that thing. And an interesting finding is that if you tell the model to optimize for lines of code, then you actually get better speed up than if you tell it to optimize for speed. At least that is the case. That was the case on LeanPool. Great. Yeah. So that golf is just really cool. It's hard to see for you. This is like maybe 100 lines of code, and this is like 4, 3. Yeah. Just really nice. This is like this is Fable. I mean, this is just one example. Fable golfed. I think it was a deletion of 10,000 lines of code and an addition of 2,000 lines of code, something like that. OK, LeanPool. I have 1 minute left in my talk, and I come to the most important part of the talk, where I would actually I actually want the most contributions from the rest of the people to this specific thing. I made many announcements on LeanPool about LeanPool on Zolib. Why is this cut off? Somehow it's cut off. OK, whatever. So yeah, you can take a look. But short story. You know how we have math journals and we have archive. And archive is kind of a very fast-moving but also shittier version of journals, if you squint hard enough. I feel that Mathlib is like those journals where the review time is 1 year. OK, Mathlib review time is not 1 year, but for journals it is. and uh, archive, you post something there, and it appears within 2 days, right? And there is a little bit of moderation. I think this is falling off. No, never mind. There's a little bit of moderation in archive, but it's really pretty minimal. I wanted to make something like archive for Lean, in the Lean ecosystem. So that's what I did. That was part of the UW Math AI Lab hackathon that we hosted in May. That was sponsored by AWS, and Lee Dimore spoke with us. That was a very exciting event. And so as part of that, I came up with this idea. And with Justin Escher, we quickly prototyped the first thing, and then I worked on it for another month. And then I told the world about it. So at this point, Lean Pool has close to 1 million lines of code. It has 144 individual projects. Each project is like paper. It's a formalization of either a named result or an actual paper, or something that is clearly has value. It's not just theory building. And my idea is that everything that leads up to that thing that has value, that clearly has value, probably also has some value. And so with Lean Pool, the idea is to just keep all of these projects under one version in one repo. When Mathlib bumps, I bump Lean Pool, and by I, of course, is all agents out. Lean Pool gets bumped. If Lean Pool gets a nice search tool, all of these projects get a nice search tool. If I ever set up a way to get academic credit for getting your project into Lean Pool, then that extends to all the projects in Lean Pool. So the idea is kind of let's herd all the cats together in one place and make it easy to find them and make it easy to depend on them.
I'm just curious, as a technical matter, when you bump Mathlib, how do you fix all the breakages?
AI.
I mean,
/goal bump. Do the bump.
okay. And that always succeeds?
Yeah, so that always succeeds. It succeeds pretty quickly. It takes somewhere between a couple of hours to 10 hours. Depends on whether they introduced a big change in the latest Lean version. And I do have a bunch of checks. So I have a bunch of linters. I have a bunch of performance profiling, which, oh, by the way, also for why might other projects benefit? Because I standardize their code. So I make sure that no file is bigger than a certain number of lines of code. I make sure that no proof is bigger than 200 lines of code. I make sure that all the Mathlib linters pass. I also golf the code. I also make it go faster. I do all of these things without changing I make sure that the statements don't change. So if statements compile, the statements have to stay. So I don't actually change. It's allowed to make new statements, and it's allowed to work on proofs. It's not allowed to do anything else. And same thing when it bumps. If the statement already compiles to the new version, the statement is not allowed to change.
You pay for the tokens. Who pays for the tokens?
Yeah, but it's so cheap. Maintaining this is so cheap. You can maintain Lean Pool on a $20 subscription.
So do you profile the code before it gets in there? So that
Correct.
the time doesn't get stolen?
Yes. So that is set up.
And then what's the limit?
What?
No turn and go back. I know what you're thinking.
Yeah. So I've rejected a few PRs because they were too slow. Yeah. And a couple of PRs because I wanted them, I told my agent to go and just make it faster, and it just makes it faster. Yes.
How quickly do you see build times growing as people add more and more stuff to this library? And
So Lean Pool is actually pretty in distribution with a bunch of other libraries. So you can see that per 1,000 lines of code, so Lean Pool is actually here. So it actually compiles quite quickly.
But that's per 1,000 lines of code.
Correct.
So as a whole, if the repository gets bigger and bigger, I assume there's some threshold where it starts being just.
When you add more code, of course, it will always take longer to compile, unless you add more cores because there's parallelization. But of course, there's still the longest poll. But with Lean Pool, the longest poll is not so bad because it's a bunch of independent projects. Anyway, so it's embarrassingly parallel. But point is, if you add more code, of course, it takes longer to compile it. But I make sure that each PR, so I profile each PR, and I make sure that it doesn't add too much. Yes?
Does Lean have like compilation caching at all?
Yes. So MATLAB has cache, which they host in Azure. I wish that I could host Lean pool on their Azure. So far, they, I mean, maybe I could ask. I haven't asked. I don't think they would say yes anyway. TauSeti is now hosted on something. I don't know if it's the same Azure or not.
Are these like huge caches, or are these like gigabyte size?
Yeah, so they're about 8 gigabytes. MATLAB is about, I think it's 8, no?
8 now? Okay. Last time.
Yeah, I think I think MATLAB cache is about 8.
That actually doesn't feel too bad for like all of math.
So Lean,
Not all of math, but like a lot of
so
math.
MATLAB is about 1% of known math. This is like the rough order of magnitude. I mean, it could be, yeah. Anyway, so Lean pool is about half the size of MATLAB at this point. It actually compiles much faster than MATLAB, like not by a factor of 2, but a factor of 4 or so. Another benefit is because the projects are independent, you can only build the one project. You don't if you want to depend on a, yeah. Oh, so my big vision with, wait, I haven't started talking about Lean pool, have I? Oh no, I have. Sorry, I just went back. Here we go. So my big vision for Lean pool is, imagine you're a mathematician or AI, whatever. You proved a new mathematical result. You want to formalize it, and you're like, well, I want to depend on some other objects. Let me see, I cite my math built on this other math. You're like, okay, does this other math, this other paper or whatever, or 2 papers, are they formalized? If you find their formalizations in Lean pool, you're like, oh, great, I'm going to depend on them, or let's say one of them, I'm going to depend on this one. I'm going to put it in Lean pool. It will import that other project. And in your archive paper, you link to that. That thing stays maintained forever. Like the versions get bumped. And this is how we can build. This is how we can get archive and Lean to kind of go in sync. This is how we get closer to the vision where every math paper in archive comes formalized. And the formalization is there, it's up to date, it's easy to find. That is my answer to this. Oh yeah, this is my answer to this question. How can the Lean community build an open source monorepo library that scales faster than MATLAB while ensuring as much of the quality as possible? Oh yeah, if you're familiar with Kim Morrison experiment of merely true, I really didn't like that experiment because there's no quality control at all. And the reason that I say scales faster than MATLAB is because I don't have a picture in my slides, but maybe you've seen the picture. If you look at the growth of MATLAB over time, it doesn't matter what metric, lines of code, declarations, number of files, doesn't matter. It looks the same. It's linear. It's actually dead on linear. That is very bad. It's not exponential. We live in an exponential world. Anything that's not an exponential, or at least polynomial with degree 2, that's not too much to ask for. Linear is really bad. At this rate, you can estimate that if MATLAB has about 1% of known math, it will take us about 100 years. It's funny to even say that, to get all known math in MATLAB, and then by that time we have 100 times more math. So that's.
How much of the theory is missing? Shouldn't you start through a dependency graph with textbooks, like GTM, graduate level textbooks? Because there's so many of them missing in MATLAB.
So that's what TauSeti does.
Okay.
So I don't have a slide here on TauSeti because I'm already way over time. But TauSeti does actual theory building. They have these roadmaps. Well, okay, I know you know, but for others, they have these roadmaps. A roadmap is kind of like an intermediate representation between some textbooks and the formalization. It's not a blueprint per se. There's no graph, but it's kind of it plays a similar role to a blueprint. Whenever anyone wants to work on MATLAB, they have to pick a roadmap. Sorry, whenever anyone wants to work on TauSeti, they have to pick a roadmap and complete milestones from that exact roadmap, not stray away. So they are doing theory building. Lean pool does not do theory building. I mean, as a side effect, it might do some theory building, but mainly it's formalizing specific results. So if some theory building occurs on the way to that, great, I'm all for it. And in the next slide, I will show you how one might discover those kind of results that are in lean pool. But the two play quite a different role.
There's no waste of this coincidental theory building. One lean pool project can read from another one, kind of deep into
It could. Right now, it's not. I want lean pool to depend on Mathlib. It already depends on Mathlib to depend on TauSeti, because the way I see it is TauSeti builds this kind of core, whereas lean pool kind of gets the leaves, right? Because you might want to have a certain known result in there, but maybe it's not kind of part of the roadmap. So I really see them as playing somewhat different roles in the ecosystem. I was actually pretty happy because when I first heard of TauSeti, essentially when I posted about lean pool on Zulip, Kim Morrison messaged me like 2 hours later. Was like, "We're working on the same thing," and I'm like, "Oh shit!" Like, of course, if they're working on the same thing, then no one will use my project because I'm not Kim. I'm not Lean FRO. But when we talked, I was actually pretty relieved because we realized that they really can coexist. So that's lean pool. Oh yeah, and if you want to contribute, please do. There are many ways to contribute. There's one way to contribute is I have these challenges, and I will add more. You can also add your own challenges. The challenge has to be something that is on the way to a big formalization project. It cannot be just some random thing. So that's a challenge. And if you want to contribute a completed formalization to lean pool, just any kind of significant result that is formalized, I'm happy to accept. So essentially, most of those like AI authored projects that are, 2 of them appear every day, like most of them I would be happy to accept, of course, after some refactor. I have a bunch of linters, and if you pass the linters, you're halfway there. And if you pass the LLM review, you're 95% there. And if you pass the profiler, you're 99% there. And then I will spend 2 minutes looking at it, and I will merge it. That's how it goes. I don't have a link here, but lean pool has exposition, and this is how you can kind of see what's in it. In reality, the best way to see what's in it is to ask your AI agent. That's nowadays always the best way to interact with anything. But if you do like a nice visualization and you like clicking things instead of typing things, so I have this exposition page, which tells you some basic stats. It also tells you the projects that we have. So for example, we have Gödel's first and second incompleteness theorems. If you click in, you can look at the dependency graph. So this is the first layer that only depends on Mathlib. This is like layer whatever. In the BFS, like if you were to do BFS starting from the first layer, going onward, that is the. Each node is a declaration. The main results are highlighted with yellow squares. This is one of the main results. This is Gödel's second incompleteness theorem. You can look at its dependency cone. So only give me the stuff that it actually depends on. So this is the dependency cone. It's much smaller. This button will not work because this will be too big. But if you go to some other file and you go to the minimal lean file, it will open. Oh, sorry, this is too large. So let me, because the problem is the lean for web, it doesn't accept a file that is too large. So that is just like an infer thing that, hopefully at some point the lean for web will fix. Oh, come on. Wait, this might be just a bug. Okay, I think this is just a bug. It's supposed to open a lean file in lean4web that has only the stuff you would need to look at to audit that statement. So all the proofs will be sorry, and any statements that it doesn't depend on, any definitions or statements it doesn't depend on, will not appear there. So the idea is someone says, I prove this, I formalized this thing, and that thing is not statable with Mathlib alone. You should be able to quickly open this minimal lean file and only look at like 200 lines of code to make sure that those 3 definitions are correct that lead up to this statement or whatever.
It's kind of what people set up with comparator, but on the fly.
No, it's a very different thing because comparator like you already need to know, like you already need to trust the statement, right? Comparator just checks that it compiles. Just it checks it better than if you just do lean build. This serves a different purpose of how do you gain people's trust in the statement. And the point is, if it's stateable in MATLAB, so it's just like one line of code or like 10 lines of code, okay, that's somewhat easy. But what if it depends on 3 new definitions that you made, or 3 new definitions and 5 new lemmas that you made? You want to kind of give them a small lean file that contains that information and still compiles. That is minimal lean file, and I swear it worked, and I don't know how it broke, but it broke. That is actually my favorite feature, so I'm pretty sad that it doesn't work now. And another thing is, if you go to declarations, you can, OK, this is like not the best way to present it, because this is just alphabetically sorted, but essentially you can search. So you can be like Gödel, incompleteness, and it's there. Right. So that's how you can see what's already in lean pool. Good. I'm almost done. I promise. Oh, I am done. That's it.
For the visualization we were just looking at, most of those declarations were not made in the Gödel incompleteness.
No, all of them are.
They are? They
Yeah.
were all made in
Yes.
the PR. Okay.
Yeah.
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 Do you have a skill to make it easier to state, like like an AI skill for making it easier to state the definitions and such?
You don't need a skill. It's good enough.
It becomes incomprehensible a lot of times. The way it'll split it up into a lot of pieces, and then it becomes hard to read.
Oh, just tell it, right? Just tell it, don't split it into many pieces. I mean, look, a skill is just a prompt.
Yeah.
And to be honest with you, most skills is just someone saying make a skill, and when to AI, and it does it. The problem is that AI, in my experience, is quite bad at prompting other AIs, unless it's like within sub-agents, because that's how it was trained for. But if you tell it like write a prompt for to do this, the problem is that it was trained on data that existed at the time, 3 months ago and earlier, where the scope of tasks that AI could do was much smaller, and the instructions had to be much more rigid. And so, if you tell the current best model, prompt yourself, or like, here's an example. If you ask a model, how long do you think it will take you to formalize a certain result? It's off by approximately 20 times. So what it can do in 1 day, it says it will take it 4 weeks. It will take it a month, something like that, or 30 times, whatever. It doesn't know how capable it is. And with skills, skill is just a prompt, except most skills are written by AI. So they're prompting themselves. They prompt themselves badly because they think that they're much more stupid than they really are. And so I don't trust more skills, especially when a new model came out and the skill has not been rewritten. That's really bad. So I don't use skills. I think most skills are bad.
This might be context dependent, but the skill is not just a prompt. The skill is a kind of like a summary of a capability, which can be dynamically pulled in. So depending on how big of a problem context window pollution is for you, it can be an effective way to fight the context window pollution by pulling in only the part of the prompt that is relevant to your task.
Yeah.
Maybe in this context this is different. I don't have experience with like clean.
Well, I'm saying that if you look at what the skill actually is, I understand that you can pull it, but what it actually consists of, it's a markdown file.
Yes, but the markdown file says this is the summary
Yeah.
of what the rest of the file will be. And at the initial load, it loads the summaries. So it has a repository of like the kind of things that's able to do. And then when it decides that it needs to actually do that, then it pulls the larger thing. So like instead of like getting all the things together, like at least that's the anthropic standard or whatever for what the skill should be. Maybe I don't know how people write their skills, but
So let's just, I haven't looked at this repo for a while, but this is the most popular repo with skills for Lean. First of all, it's way too much.
You don't use this?
No, I don't. So so this is a skill that does axiom elimination. So let's look at it. I don't want this in my prompt. It already knows that. Sure, okay. Can you see? Maybe this is too small. Okay, this is just whatever command they defined. I mean, it knows how to do /print. It doesn't need advice in that. Using axiom checks. So again, this is a script they wrote. So
there is no separation between like the thing that's loaded dynamically and the thing that's like.
No, it will load this dynamically. Like it will, if you tell it like eliminate axioms, it will load the skill.
No, that's not what I mean.
I mean, it's more of a skill versus memory issue, though. I mean, I guess the question is, would you put anything in the memory, I suppose?
No.
We might have veered too far from the
So I don't use I don't use any custom prompts, any harness, any nothing. You don't need anything like that. It's all just propaganda. It's what Jesse Hand wants you to believe that allows him to prove sphere packing, but in reality you just prompt Opus 4.5 at that point, I guess, long enough and it does it. And yeah.
Back to the Mazur's theorem. So in your big formalizations, I guess, I don't know how carefully you looked into it, but like that plan of getting the agent to write a plan and then just follow it. Often what I've seen is there's mistakes in the plan. You have to change the graph.
Yeah.
I guess you're planning for that, you're thinking the graph is good. Like, does that, are you thinking about that as you ask? Especially if you get other contributors, like that dynamism of like, okay, now we need to create new nodes, you have to pop some nodes. Like, what's the plan there?
Oh, I think it's very simple. How do humans do this? Someone notices that it's wrong, and they change it, and the AI should do the same.
So, but you can create trashing, right? Should there be like a more central authority that owns the graph versus if all the contributors?
I think it's solving a problem that doesn't exist.
Okay.
Yeah. Yeah. Any other questions? Yeah. Yeah.
So, what kinds of contributions would you most appreciate for Lean Pool? Like, what would be most valuable for you?
Anything. Just have fun with it, right? You probably do some formalization yourself if you're here, or maybe you want to do some formalization. You probably use AI. Just like, I don't know, like maybe you studied some math back in the day and you want to formalize it. Tell your AI to do it, and then be like, okay, what's like a major result in that area? Formalize it and then just PR it. Like it's kind of all up to you. I mean, I really don't like how gate-kept mathlib is. I feel that even Tau Ceti is too gate-kept. My Tau Ceti roadmap PR has been sitting unreviewed for 2 weeks now. I don't know who makes the decisions, which roadmaps to review and which ones not to review. But like without a roadmap, you can't start formalizing. I don't like it. I think that I want, not all of us are Kevin Buzzard. Like not all of us know all this like complicated math. I'm a math PhD. I know some math, but like I'm nowhere near as good as those mathematicians. Like I know my little niche, and I don't know much else beyond it. But that should be okay. We should still be able to participate in this process. So I'm just really happy when people contribute in whatever way they want, and I really want a discussion around it. I think this should be like a really community-driven thing.
So if I understand you correctly, you're accepting submissions at all functional scale. So the recent result, a couple of foundational theorems, a whole textbook, a dictionary. If I could go ahead and formalize my encyclopedic dictionary of mathematics, Lean Pool would accept that?
No.
No. Okay, so there is some, there is...
It has to be one thing, one named theorem, one paper. One textbook is too much. It's too
So
disorganized.
there is a scale limit. Okay.
It's not about the size. I have several PRs that I've merged that are 50,000 lines of code, but they lead up to a specific named result. And actually, to be fair, some PRs that I've merged are not like that. I just they contain some significant result that I want to have, but they contain other stuff too. So it's not a perfect rule.
Right.
But if you go and formalize a dictionary, that's just, well, first it's not math. Dictionary is not math, right? Unless what kind of dictionary?
I'm thinking of are.
Like what kind of dictionary?
So there's the Encyclopedic Dictionary of Mathematics that was made by the Japanese Mathematical Society about 40 years ago and translated by MIT Press, I think 1978 or something like that. It's got a lot of very good, concise articles for covering about, I don't know, 2,000 subjects, 2,500 subjects, and each of those would be a good representation. They might be a nice little piece, but they might all fit together, and it might be interesting to do some kind of analysis whether there's duplication. There are other dictionaries which go ahead and list a number of terms that are used in English literature that are common among various...
Okay, I understand. So just tell your AI to make a PR, and we'll talk about it.
Okay, but I just want to get a rough idea as to scale, because one of my first choices, if I were so inclined, would be to take my general algebra textbook from 20 or 30 years ago and submit that to Lean Pool, not because it has a single particular theorem, but because it has a corpus of stuff that I could use for my development in general algebra.
Sure, if it's not in MathLib and it's a significant piece of math, PR it.
Right, but it sounds like the significant piece of math you're used to seeing are single papers or results or collections of related papers.
Just submit whatever PR and we'll see.
I see. Okay, thank you.
Yeah. I really want to be very, very inclusive.
Okay.
Yeah.
Did the recent soundness bug affect Lean Pool? Did you upgrade the compiler? Did you see anything?
So Lean Pool is at 433 RC1, which does not have those patches because even MathLib doesn't have those patches yet, at least not all the ones that OpenAI helped find. So it's impossible right now to bump to a completely sound version, and, well, completely... No, not at all, because I think it's completely overstated. I think in reality, it's very specific things in very specific meta programs, and if you don't have those specific meta programs, then you can be sure that you don't have that specific issue. You cannot be sure that there might be some other bug that affects it, but it's very easy to see that one, is not there. Yeah. Anything else? Yes.
This is a bit, to wrap things up. I was asking our friend from OpenAI about his timeline of when he thought all of mathematics would be formalized, going back to the first slide.
Yeah.
And he said 10 months, I believe, a little bit less than a
year.
Yeah,
I would agree with that.
You would agree with that?
Yeah.
It was interesting in your timeline.
Yeah, I think that sounds about right.
Start a vote in the Discord.
Yeah, that sounds about right. So I have a bet with Brian Nugent where he said it will not be done in 5 years. To me, that's completely insane. I think 2 years is pretty conservative, and I think 1 year is pretty realistic.
Can
and
you define all of that a little bit more?
Yeah, I have a maybe you have. How about you start? I have my own definition.
Well, actually, I haven't thought that much about classifying all of mathematics. I am pretty okay with your definition because, again, I do agree that, everything that has been done in the last 50 years contains everything of importance in the background that was done previously. So it's sure, if we can get 20 million results, I formalizing Lean, I would probably say, 99% of mathematics has been formalized.
Yes.
I would be okay with that.
Yeah, I see. So I think if you just look at the number, it will be misleading because There are many declarations in MATLAB that do not correspond to any kind of theorem in a paper. It's much more kind of granular, more low level, like a lot more intermediate results that you wouldn't ever see in a paper. Here's my definition of, and I don't want to all is a provocative. So yeah, now that the talk has ended, you see that, okay, my title was pretty provocative. I like it this way. So I really don't like to think about all. I like to think about the core. And how I define the core is that when a new archive paper comes out, sorry, it doesn't have to be archive, sorry, just like new math paper comes out, they will define some things and they will assume some things. And the things they define, they might have been defined in other papers. But the authors have some sense, being experts in the field, they have some sense about what other experts in the field know and what they don't. Whatever they don't feel the need to define explicitly, those things have to already exist, or like have to be very trivially statable with the existing core. Like if that is true for, let's say, 90% of new math papers that come out, that like all of the kind of stuff that they assume and they don't explicitly define, like then I would say we're there.
Explicitly define is like mathematical definition.
Okay. Do you think it's something that has a long tail or something that has a very abrupt end? Like, is it something that we're going to get close to 99% of mathematics being formalized and then the last 1% is going to take like as much, or it's something that is going to completely collapse the moment that it gets to a certain point? It's like all of a scale.
No, I think that, look, in 3 months, you've seen the progress, right?
Yes.
To me, that's completely astonishing. It's essentially like 1 or 2 generations of models. Yeah. Right now, we're not. I think if the current model progress stopped, we wouldn't get there in a year. It would take quite a bit longer. I guess I'm pretty bullish on how much better the models will get. Okay. And then the issue will really not be intelligence anymore. I mean, even now, I would say that the bottleneck really is not intelligence. I would say that now the bottleneck is the order. The order in which you do things and how you organize it. It really became a logistical and social issue, not an intelligence issue. That's why I started Leanpool, because I feel that someone has to, and really I think it should be LeanFRO or MATLAB Initiative. And I'm amazed that it took them so long to get there. That some random guy like myself made Leanpool before they made Tau Ceti. Like, to me, that's incredible. But anyway, they have Tau Ceti now. It's not growing very fast, surprisingly. It really should grow much, much faster. So it comes down to us, the community, who are interested, the enthusiasts, to pick a thing and formalize it and somehow make sure that it becomes discoverable, that it gets into Tau Ceti, into Leanpool, something. I think a big win, I think the first big win we will see is when some AI formalization gets dependent on, becomes a dependency of something else. So for example, there's edcombi, which is, I think it's Yael Dallas, I think it's his, do you know? Anyway, it's like additive combinatorics, whatever. It depends on MATLAB, but then a few other projects depend on it. If Tau Ceti becomes something like that, where like there are several projects that depend on Tau Ceti, that might be human authored, might be AI authored, like that is a win. So far, we haven't seen a single example where AI generated code is a dependency of some other formalization. To me, that's really sad. But I think we should change that.
All right.
Yeah.
So yeah, going back to the first, like the second question, it's like you think that it's not going to have a very long tail. Like the moment that we get very close to 100%, it's like just a matter of a few months more to get to 100%.
If anything, it has a long, the opposite of a tail is nose. It has a long nose. It's very hard to start.
Yes.
Like right now, we're in this like very slow start period where people on Zulip are still like, what's the point of Tau Ceti? What's the point of
cards? Because like it's very slow at first, but then everything collapses at once.
Yeah, except it's not collapsing but building.
Yes, But
So if you take House of
you get the
you take House of Cards, if you take House of Cards, but then you reverse the video.
yes.
Yeah.
Sure.
Yeah. Right.
There's an actual fan out further down. We're still like in some fields of math. But
Yeah, but
At some point we'll have like enough enthusiasts and well enough built pipeline that like, I mean at some point there will be companies like probably Axiom would be interested in just like giving money to like, hey, like, Tau Ceti, you guys are good at like formalizing stuff. Just like, here's 50K, I want that result in Tau Ceti in 3 days, please.
The PDF to Axiom pipeline is real.
What?
I said the PDF to Axiom pipeline.
What is that?
Where you have a PDF,
Yeah.
a crusty PDF, and you throw it in a pipeline, and it produces lean axioms.
Here. It produces an entry for lean pool.
Yeah, so I mean, if you erase.
Wait, what's the point of producing axioms? I don't understand.
Theorem.
Theorems.
PDF.
Well, when I write it, they're axioms, but when you write it, they're theorems.
But like
Hopefully that
axioms you
clarifies.
don't prove. So I don't understand what you mean by axiom.
So an axiom is something that you assume
Right.
because it's not proved.
Right.
So I made a joke and I said, you probably make theorems, but I'm making axioms.
Okay, I still don't get it, but it's fine.
I'm sorry, I just confuse people with wordplay.
Okay, it's fine. Sorry.
Any final question?
Yes.
Just a real one-edge case regarding where intelligence might still be a bottleneck. Like, there have been very important papers in medical history that weren't necessarily wrong, but very, very sketchy. Like the original
Of course.
of the longer range.
That's why we formalize.
Yes, but I'm saying like filling that in isn't. I do expect that there will actually need some non-trivial intelligence increases to formalize some of the really sketchy geometric work that is out there. For example.
Yeah, I think it's much easier to fix a proof that is mostly correct and has a few gaps than to come up with the proof in the first place. And we see that the models are good enough to come up with incredible proofs in the first place. So I'm not so worried about that. Of course, if the proof is completely broken and it's not fixable, that is very rare, by the way. But if that happens, sure. I mean, that is the original motivation for formalization. If we have some result that like everyone's like, yeah, of course it's true, but like just not enough people kind of like looked at all the details, and there is one small detail that is so wrong that it just doesn't work, and somehow no one noticed down the line, no one errated a contradiction. I mean, that is a very, very low probability chance, like low probability event, but if that event happens with some big branch of math, that would be pretty devastating. So we kind of want to discover those, I think.
Are there any examples of those that have happened?
I don't know of any. Does anyone know?
Specifically,
Like finding
Oh, errors, of course, but like,
Examples of results that were proven and that walked back. I know Spale told me of a few examples.
but they were all fixed, right? Like I don't know of anything.
There are theorems that have been accepted and got like the Lenin Prize, like the highest math prize in Soviet Union.
Yeah.
10 years later, some seminar, graduate students finally read the thing. It was wrong. There's a case of Daniel Lurie, a PhD from Harvard,
Yeah.
high profile, all of that.
Uh-huh.
One of the lemmas is like irrecoverably wrong. Bunch of papers full. There is the
I see.
Machiavelli thing, which is like you can think
Yeah.
controversial, but like
Yeah.
mainstream
I guess,
opinion just is
like, which ones, like, has any one of them been depended on by a bunch of other people?
Yeah, I think the Lenin Prize one was probably.
Okay, I see. So that's a good example.
I mean, again, it's not my field.
Yeah. Yeah, thanks.
So, I mean, again, the levels of, it varies.
Yeah.
Yeah, and most of the examples that I've encountered are pretty much end results. And there's a lot of work there, and not much has been developed upon these results. But some of them are wrong, and some of them are known to and not very widely publicized. I'm afraid I don't have any current examples.
Yeah, like the few math papers that I've reviewed myself, I think there's been a mistake in each one, but they're small mistakes.
There are also things that are like stated results that are very hard to sweep under the rug as small mistakes.
Right, yeah,
But
that's fair.
They exist, and you can probably find some of them if you take a look at the appropriate fora and do a general search, because a few people have talked about them.
I see. Yeah, that's fair.
Could you do me a favor? Could you look up Encyclopedic Dictionary of Mathematics on your system there? and I think this is a reference that I really liked. And if you're not aware of it, I think you should at least see it. And the version I have was published by MIT, but it was based on a Japanese version that was printed some years earlier. And yeah, this looks like it.
Is it like the Japanese Bourbaki?
No.
No? Okay.
But there are some comparisons you can make.
I see.
Take your favorite paper. Your work was on what? Fluid dynamics?
Plasma simulation. Actually, I did applied math mostly.
You know what? That no skin off your nose. So you could probably summarize a lot of your stuff in a nice little article there. That's about one of 2,000 or 3,000 articles they have there on various branches of the subject. So you know of the mathematical science classification that's got like 100 main categories and then
Yeah, sorry, I'm gonna interrupt you because I think we're veering to the off topic, and let's continue the discussion after people leave because I think this.
Except that you said all math.
Yeah,
So
make a PR. Make a PR.
Is to try to get 10% of EDM into the.
I'm not gonna do that, but you can make a PR.
Okay.
Yeah, thank you.
I think it's almost 9 o'clock too, so I think let's take the speaker one more time.
Yeah, thank you.
Continue the full conversation.
Yeah, it was super nice to meet all of you. If you want to chat, I'm happy to chat. If you want to message me on Zulip, message me on Zulip.